adhere to these kind of thought process related to consistency, partitioning, storage layout, or a query model. So let's begin. And this might be too technical for some people and might be easy for some. So now we'll start first of all by building a concept around the CAP theorem, which is coined by Eric Brewer in 2000 and which is widely adopted today. The theorem states that within a large-scale distributed data system, there are three requirements that have a relationship of sliding dependency: consistency, availability, and partition tolerance. Now, consistency means that all database client will read the same value of the same query, even in case of concurrent updates. Or we can say that all nodes see the same data in the same time. So, availability, and especially high availability, meaning that a system is designed and implemented in a way that allows it to continue operations, read and write, in case of a node crash or some hardware or software part down due to upgrade. Now, coming to third, which is partition tolerance. The database can split into multiple machines. It can continue functioning in the face of network segmentation breaks. It also understood as the ability of a system to cope with the dynamic addition and removal of nodes. Now, one can at most choose two of these characteristics in a shared data system. So these three circles are trying to depict that they're not intersecting altogether. So it's intersection of consistency, availability, and partition tolerance, and consistency and partition tolerance. Now this triangle trying to tell us that what are the scores are in which area. So we have a combination of consistency and availability in relational databases, a combination of consistency and partition tolerance in case of Neo4j, Google Bigtable, and its derivative MongoDB, and etc. Same goes with availability and partition tolerance. We'll see more combination and more traits in our next slide. Now, this is a kind of a chart which depicts that how will trace it out if a system is in a distributed environment. So when a system says CA, consistency and availability, means that we are likely using two-phase commit for a distributed transaction. It means that system will block when a network partition occurs. So it may be that system is limited to a single data center cluster in an attempt to mitigate. Now coming to second combination, which is CP, and to primarily support consistency and partition tolerance, we may try to advance our architecture by setting up data shards in order to scale. Our data will be consistent, but we still run the risk of some data becoming unavailable if nodes fail. Coming to AP, which is to primarily support availability and partition tolerance, our system may return inaccurate data, but system will always be available. Now, even in the face of network partition. So this table is trying to depict that. Now, coming to our important comparison between ACID and base. Now, base forfeits the ACID properties of consistency. Those who are working on RDBMS system, they are quite familiar with the ACID properties of consistency and isolation. So base favors availability, graceful degradation, and performance. So it's a trade-off between ACID and a base systems, and proposes a decision criteria to select one or the other for individual use cases. If a system or part of a system have to be consistent and partition tolerant, ACID properties are required. So I will repeat again. If a system or part of a system have to be consistent and partition tolerant, ACID properties are required, as we see in the triangle. And if availability and partition tolerance are favored over consistency, the resulting system can be characterized by the base properties. Now, Google Bigtable chooses neither ACID nor base, but the third CAP alternative, being consistent and available system, and consequently not be able to fully operate in presence of network partitions. So a bit on strict consistency and eventual consistency. So strict consistency means all read operations must return data from the latest completed write operations, regardless of which replica the operation went to. Such a strict consistency cannot be achieved together with availability and partitional tolerance according to CAP theorem. So we can choose only two. Now coming to our second point of eventual consistency, means the reader will see writes as time goes on in a steady state. The system will eventually return the last written value. Clients therefore may face an inconsistent state of data as updates are in progress. For instance, in a replicated database, updates may go to one node which replicates the latest version to all other nodes that contain a replica of the modified database, of the modified data set. So that replica nodes eventually will have the latest version. So this is how eventual consistency can be conceptualized. Now we move on another interesting concept of versioning of a data set in a distributed scenario. Now this is fairly important because if data set is distributed among nodes, they can be read and altered on each node. And no strict consistency is ensured by a distribution transition protocol. Question arises on how concurrent modification and versions are processed and to which value a data set will eventually converge to. There are several options to handle these issues. Obvious ones are timestamps and optimistic locking. Now, timestamps rely on synchronized clocks and do not capture casuality. Some of the NoSQL store example, Cassandra, uses timestamp at the column family level to determine the most recent value when doing read request. Optimistic locking does not work well in a distributed and dynamic scenarios where servers show up and go away, often and without prior notice. So optimistic locking is used by database system like Google App Engine, MySQL as a DBMS, which only implement optimistic locking. Implement a layer outside the database like Ruby on Rails, Hibernate, Microsoft Entity Frameworks. So these supports optimistic locking, but there are others like vector clocks. Now, vector clocks are an alternative approach to capture, order, and allow reasoning between updates in a distributed system. A vector clock is a list of node counter pair. Every version of every object is associated with one vector clock. Now, if the counter on the first object clock are less than or equal to all of the nodes in the second clock, then second is the latest updated record. So, example from the NoSQL store, Amazon Dynamo and React, which are using vector clock kind of versioning. Third is multi-version storage, which means to store a timestamp for each table cell. These timestamps do not necessarily need to correspond to a real life, but can also be some artificial value that can be brought into a definite order. For a given row, multiple versions can exist concurrently. Now, example of multi-version storage are Apache HBase, CouchDB from NoSQL world. Even MySQL, when used with NoDB, and Sybase and Oracle provide multi-version storage. Now, partitioning. So we have seen that assuming that data in a large-scale system exceed the capacity of a single machine and should also be replicated to ensure reliability and allow scaling measures such as load balancing. Ways of partitioning the data of such a system have to be thought about. Depending on the size of the system and other factors like dynamism, there are different approaches to this issue. So when I say dynamism, it means that how often and dynamically storage nodes may join and leave in a distributed environment. We'll see an example ahead to visualize these effects. Now, so the first one is the memory caches. Second is clustering. So in case of clustering, client should not notice talking to a cluster of a database server instead of a single server. So clustering features have only been added on top of RDBMS that were not originally designed for distribution. This is what a lot of people, a lot of critics is going around. Now, third approach is separating reads from write. Now, this is a master-slave kind of an agreement, and the replication of data can happen either by a transfer of state or by transfer of operations. which are applied to the state on the slaves nodes and have to arrive in the correct order. Now, but we have to be cautioned around master slave, but we have to be cautioned about master slave scaling features. And master slave failures, now sharding is another concept which means to partition the data in such a way that data typically requested and updated together resides on the same node, and that load and storage volume is roughly evenly distributed among the server. So with sharding, we lose all the features that make the RDBMS useful, and that sharding is operationally obnoxious. This valuation refers to the fact that sharding was not originally designed within current RDBMS, but rather added on top. In contrast, many NoSQL databases have embraced sharding as a key feature, and some even provide automatic partitioning and balancing of data among nodes. Example, MongoDB. Now we look around another concept of consistent hashing. This is important because the downside in a distributed environment of sharding is that at least part of the data have to be redistributed whenever a node leaves and joins. So in a memory caching scenario, like the first case of partitioning, data redistribution may happen implicitly by absorbing cache misses, reaching data again from database or backend system, hashing it against the currently available cache server. But for a persistent data store, this implicit redistribution process is not acceptable, as data not present on the available node cannot be reconstructed. So we'll see to visualize this thing. Now, so we are saying in consistent hashing, we are hashing not only hashing object but also machine has the advantage. So we'll briefly visualize how this is happening. So there are 3 red color nodes, A, B, and C, and 4 blue colored objects that are mapped to a hash function. Result range to a hash function result range, which is imagined and pictured as a ring. So we can see that. Now, which object is mapped to which object is determined by moving clockwise around the ring. So object 4 and 1 are mapped to node A, object 2 to node B, and object 3 to node C. Now, when a node leaves the system, the cache object will get mapped to their adjacent node in a clockwise direction. So I'm just taking a taking a scenario that I'm mapping all the nodes in the clockwise direction. There are specific algorithms specific to different NoSQL data stores which map it differently, but the concept remains same. Now, and when a node enters the system, it will get hashed onto the ring and will overtake object. Now, let's see. So node C and node C left and node D entered the system. So that's now object 3 and 4 will get mapped to node D. This shows that by changing the number of nodes, not all objects have to be remapped to the new set of nodes, but only part of the objects. Now, we'll see about membership changes as we are discussing about node joining in and going out of the ring. So in a partition database where nodes may join and leave the system at any point without impacting its operations, all nodes have to communicate with each other, especially when membership changes are happening. So let's again visualize the same scenario. We see that node X joins a system for which a replication factor of 3 is configured. Now it is hashed between A and B, so that the nodes H, A, and B transfer data to the new node X, and after that node B, C, and D can drop part of their data, for which node X is now responsible as a third replica, in addition to node H, A, and B. In a similar fashion, when a node leaves the system, the following action will occur. So the action to be taken when node B, due to crash leaves the system. Nodes C, D, and E become responsible for new intervals of hashed object and therefore have to copy data from nodes in counterclockwise direction and also recognize their internal representation of the intervals as the range AB and range BC now collapse to range AC. So moving ahead on storage layouts, where we will see an overview of storage layout which determine how the disk is accessed and therefore directly implicate performance in case of a database. Now, the first kind of a storage layout is a row-based storage layout. Means that a table of a relational model gets serialized as its lines are appended and flushed to disk. Now, the advantage of this storage layout are that at first whole data set can be read and written in a single I/O operation, and secondly, one has a good locality of access of different columns. Now, on the downside, operating on column is expensive as a considerable amount of data has to be read. So example include MySQL and PostgreSQL. They have a row-based storage layout system. Moving to our second is columnar storage layout, which talks about serializable tables by appending their columns and flushing them to disk. Therefore, operations on columns are fast and cheap, while operations on rows are costly and can lead to seek in a lot or all of the columns. A typical application field for this type of storage layout is analytics, where an efficient examination of columns for statistical purposes is important. Example include KDB, SAP HANA, Microsoft SQL Server 2012, Enterprise Edition. Now, a third kind of columnar storage layout with locality group is similar to column-based storage, but adds the feature of defining locality groups that are a group of columns expected to be accessed together by clients. The columns of such a group may therefore be stored together and physically separated from other columns and column groups. Examples include Apache, etc. Now, these are important as I've mentioned previously that they will directly implicate the performance. Now, we'll quickly run through the query models, which is there are substantial differences in the querying capabilities between the different NoSQL database data stores. Now, key value store by design often only provide a lookup by primary key. Document databases, CouchDB and MongoDB allow for complex querying. Some column family stores like Cassandra offer range query. So this is not surprising, as in the design of many NoSQL databases, rich dynamic querying features have been omitted in favor of performance and scalability. On the other hand, also when using NoSQL databases, there are use cases requiring at least some querying feature for non-primary key attributes. So we'll see some of those workarounds which we can do, and so two kind of models listed. So one is companion model, is an approach in which searchable attributes are copied to a SQL or a text database. The querying capabilities of this database are used to retrieve the primary keys of matching dataset, which the NoSQL database will subsequently be accessed. Second kind of model is scatter and gather local search, which can use the NoSQL store, allows querying and indexing within database server nodes. If this is a case, a query processor can dispatch queries to the database nodes where the query is executed locally. The result from all database servers is sent back to the query processors for post processing them, like aggregation and returning the result to a client that issued the query. So we see, as we are ending it now, the final comments. Now, each NoSQL database has its own strengths and weaknesses. Analysis of system requirement is therefore crucial to ensure that the NoSQL database and unlisted can be a good fit. So, NoSQL is typically good for unstructured schemaless data. Usually, we don't need to explicitly define a schema upfront and can just include new fields without any issues. Now, NoSQL typically favors a denormalized schema due to no support for joins for the RDBMS world. We would usually have a flattened denormalized representation of a data. Using NoSQL does not mean we lose data. Different DBs have different strategies. For example, MongoDB can essentially choose what level to trade off between performance and potential data loss. It's very often very easy to scale out NoSQL solution. Adding more nodes to replicate data offer more scalability and also offer more protection against data losses if one node goes down. But again, depends on NoSQL DB configuration and the kind of vendor we are used to. So so relational databases are no longer a default choice, and flexible data store of NoSQL can speed up our development. So that brings to an end of our session. I hope the technical part was somewhat understandable. So these are the references. You can Q&A. Sure.